So I will be introducing Project GUHeat. So my name is Ariel C. Blanco from the UP Department of Geodetic Engineering and Training Center for Applied Geodesy and Photogrammetry. So the outline of my presentation is as follows. So we will look at what urban heat island is, the impacts that have been mentioned by Dr. Paringit, and discuss about Project GUHeat, its objectives, project size, and activities that have been conducted so far, as well as some selected studies and outputs, including maps and tools. So first, let us imagine this, one hot sunny day. Imagine or remember how hot the surfaces could be or could you could feel these surfaces. You have concrete, you have grassy area, you have water in a sandy beach, or you have also wood. I'm sure you can imagine how hot these surfaces could get. If we look at the different cities, particularly, for example, in this case, the BGC area, we see that a city is composed of buildings, structures, houses, urban parks, vegetation areas, roads, etc. And these are consisting of different materials which retain heat in different ways or dissipate heat at different rates. So urban heat island is defined as a phenomenon which results for having higher air or surface temperature in urban areas or cities relative to their surroundings. You can see in this diagram, rural farmlands and rural areas would have relatively lower temperature, particularly in this diagram, late afternoon temperature. But as we increase the density of built-up areas, as we increase the geometry or because of the different geometries of these urban areas, some areas like the highly urbanized ones with tall structures and high density of areas will have very high temperature relative to its surroundings. In this figure, we can see another depiction of the urban heat island effect. It occurs when a city experiences much warmer temperatures than nearby rural areas. We can look at urban heat island, for example, within city or intercity or inter areas within cities or municipalities even. Here we can see that you have rural farmlands of urban residential parts with different variations in the content or in the distribution of vegetation in the built-up areas, as well as the urban residential, downtown areas, and so on. UHI is known to affect local weather, climate, and impacts urban development and human living. So one of the main impacts would be in producing secondary effects on local meteorology, including altering the wind patterns, even the development of fog, humidity, clouds, and the rates of precipitation. It is also known to correlate well with increased concentrations of air pollutants. So these pollutants include volatile organic compounds, carbon monoxide, and other pollutants in the air. So in this figure, we can see that you have an area of Metro Manila covered with high particulate matter and other air quality problems. So UHIs also have the potential to directly influence the health and welfare of urban residents. So if we look at here in the news clipping, so 2 died from heat stroke as Cagayan Valley records highest temperature. And based on the country and the health profile of the Philippines in 2015, under a high emission scenario of climate change, heat-related deaths in the elderly are projected to increase to about 31 deaths per 100,000. This is in 2080. So this is very high in comparison to the estimated baseline of 1 death per 100,000 annually between 1961 and 1990. Another consequence, as pointed out also by Dr. Paringit, is the increased energy required for air conditioning and refrigeration in cities that are comparatively hotter. Today, approximately 20% of that electrical total electricity is used in buildings around the world goes towards air conditioning units and electric fans. In the graph below, we can see the world energy consumption for space cooling in buildings. And this has increased threefold or from 600 terawatt per hour to around 1,800 or 2,000. And the increasing share of the total final energy is attributed to the cooling systems. The geospatial assessment and modeling of urban heat islands in Philippine cities was a project approved by the Department of Science and Technology, Philippine Council for Industry, Energy, and Emerging Technology Research and Development, and implemented by the UP Training Center for Applied Geology and Photogrammetry. So in collaboration also with the PAG-ASA. So we started in January 16, 2019, and we are ending on August 15 rather, 2020. Our project aims to assess the development of urban heat islands in rapidly urbanizing and highly urbanized cities in the Philippines and develop models for estimating land surface temperatures, and we extended this to air temperature, and predicting urban heat islands by creating different models relating the factors such as land use, land cover, material distribution, and other things to land surface temperature and air surface temperature. We have several actually specific objectives, but I represented the keywords in this word cloud. So we are looking at the pattern, the trends. We are characterizing land surface temperature, urban heat islands. We are developing the databases. We have developed databases. We have produced maps and models. And soon we will be making available geospatial toolbox to enable LGUs to utilize these particular maps and models. And we are actually looking at also studies linking or assessing the impacts of urban heat islands in different cities we have mentioned. In addition, we are doing a lot of microclimate simulation, small scale, different parts of the cities in order to examine the dynamics of this air and surface temperature, as well as the development of UHI. And we have conducted several surveys on thermal comfort. But ultimately, the game or the goal is to through the capacity building of SUCs and HEIs, as well as our partner LGUs. The aim is to integrate this within the planning process and identify, implement mitigation strategies in order to reduce the currents and even the growth of these urban heat islands. Here we see, we have mentioned land surface temperature. Here we see an image, Lancet image showing Metro Manila and surrounding areas. And the image in the middle shows the thermal image. So ranging in this case, 23 degrees Celsius to 43.13. Comparing these two images, we can see that as expected, we have urban areas with higher man-made structures being higher in temperature and areas dominated by vegetation having low temperature. So if you look at, for example, this daytime land surface temperature of Malabon City, we can identify some hotspots. These hotspots correspond to very dense urban areas, can be residential, can be combination of residential and other uses. And then we can also see cold spots as well. So with lower temperatures surrounded by lower temperatures. So fish ponds and mangrove areas, for example, in Muson, Malabon, represent a colder area. In Project GUHeat, we are also looking at nighttime land surface temperature. So in this case, we have seen we can see in the left image, the 30-meter resolution daytime LST map derived from Landsat. And the pattern is different if you look at the nighttime land surface temperature of Quezon City. This is primarily because of differential heating, differential cooling rates, of these different surfaces. In the left image, we can see the reservoir, the Mesa Reservoir, as having low temperature relative to its surroundings. But in nighttime, you can see it to have higher temperature. In the nighttime, also, we can notice the patterns, no? The roads pertaining to the roads, which are warm or relatively warmer compared to the other areas which have already cooled down. So Project GUHeat is also implementing algorithms in order to produce higher resolution land surface temperature maps, such as this one, showing the area of UP Diliman campus. And then we are utilizing also thermal cameras, which we deploy in drones or in mounted on tripod and placed on top of buildings to monitor the dynamics of the land surface temperatures of rooftops, of vegetation areas, and other things which we can see in the neighborhood. So these are useful in order to validate the temperatures that we see from the satellites, or we estimate from satellites, as well as for the numerical and the simulations that we are doing at the microclimate level. Project GUHeat, as stated by our host, is implemented in 7 cities. So we will show here from here on, I will show some images, Google Earth images in perspective, in 3D perspective, showing these cities. I would like you to notice or take note of its surroundings. Is it surrounded by a body of water or adjacent to it? Or you can see the differences in the terrain or elevation and so on. So here we have Zamboanga, one of the project sites, and we collaborated with Ateneo de Zamboanga and the city of Zamboanga, or LGU Zamboanga City. So zooming in into Zamboanga, we can see these different patterns of urban development, as well as the areas which are for housing, etc. And Paseo del Mar here is shown, which is one of our site for microclimate simulation. In this slide, we can see Davao. So Davao is the largest city in terms of land area. So we can see here much of the green areas, but we can see concentrations of built-up areas near the coast. So here we collaborated with University of the Philippines, Mindanao, and of course, LGU of the city of Davao. Again, if we zoom in into this area, we can see Davao River, we can see areas of different densities of built-up structures, as well as areas which are dominated by grass and trees. Next, we go to Cebu, Cebu City. So here, Cebu is basically a coastal city also, similar to Davao and Zamboanga City. But here we can see also massive or expanse of built-up areas, but they are adjacent to mountains and hills. So here we collaborated with the University of San Carlos and of course the city of Cebu, LGU. Zooming in, so we have this picture or image of the urban density in Cebu City. Adjacent to it, we have the city of Mandaue, much smaller compared to Cebu City, but very dense and full of buildings. So here we collaborated with the University of the Philippines, Cebu, and also with the LGU of Mandaue City. Zooming in, we see here some mangrove areas and different densities of built up or development. For Iloilo, Iloilo is relatively flat. And here we collaborate with the UP Visayas and the LGU of City of Iloilo. And we can see here that Iloilo is quite unique also, or maybe be similar in a way to other cities, but it's near a body of water, 2 bodies of water. You have the river and then you have the strait. And the main difference maybe will be the topography, which is actually less varying compared to other cities. So I mean, we have this one. So in Project GUHeat, we are not only looking at urban heat islands, we are also looking at also the cooling effect, urban cooling islands as well, of these, say, wetlands. No? So for Metro Manila, we are focusing primarily on Quezon City. So the densest, the biggest city in the Metro Manila. So thank you to all of the LGUs. We collaborate here with Quezon City LGU. And zooming into this area, we can see the University of the Philippines campus, the elliptical and the parks, as well as the different densities of residential areas, the UP Village, Katuna Village, as well as other areas. So you can imagine these areas would have different thermal characteristics because of the patterns, the distribution, the arrangement of these built-up structures together with the vegetation areas. Next, we go to an area or city at high altitude, Baguio City. So the summer capital of the Philippines, we collaborate with University of the Cordilleras and LGU of Baguio City. And if we zoom in here, we can see the massive and extensive built-up areas surrounding Burnham Park in Baguio City. So Project GUHeat, so I would like to walk through to the different GUHeat activities. So first, of course, we did several meetings with our partners, including those from which we are asking data. For example, in this case, we signed an electric company, and of course, meetings with the different LGUs. And we can see also that through this project, we have different capacity building activities, primarily for state universities and colleges, HEIs, and also with the LGUs in different project cities. So this would have planning activities as well as training on the various stages of the project. Of course, we have conducted various field surveys. We collected temperature readings and of different materials. We have installed air temperature sensors to continuously monitor the air temperature in different areas in order to provide data and validation data for our microclimate simulation. We also did mobile air temperature and particulate matter measurements to see how the different patterns of in the urban development would correspond to air temperature or how they affect also the PM 2.5 concentrations. So in our project, we have to look at or characterize the 3D character or the nature of the cities. So we use drone surveys to do that. And this drone surveys will provide us a 3D models, orthophoto, and also digital surface models. In the field, we also conducted or did some simulation or survey, laser scanning survey, to have more detailed information about the 3D geometries present within certain parts of the cities. So these are necessary for subsequent modeling and simulations. Whenever we meet with our partner LGUs, maybe towards the end of this project, we have been distributing maps to different LGUs in hard copy and also in digital format so that they can use in their geographic information systems. Okay. So our study, as mentioned, by focusing on the different 7 cities that I have mentioned, we are extending it, of course, to Metro Manila and also to the entire Philippines. But of course, several studies like the digital simulation will not be possible because of time limitations. But for example, here we have extended it for Metro Manila. What we are seeing here in the middle figure are some red, no, color red, showing transition or the hotspot areas or transition to hotspot areas. So we can see here that the dynamics of these urban heat islands. No? So in this case, the hotspots or the red areas and the pink areas would be those urban heat islands. No? They can actually persist over time. They can also disappear for a while, then return as well. But if we have a summary of that, so that is shown in this right figure to the right, we can see these areas which are actually relatively more persistent UHIs within this city. So this is the work of Landicho. So as I've mentioned, we have mentioned the importance of the combination of the structures, whether high or low, the built-up structures interspersed with the vegetation areas, grasses and trees, and so on. For that, if these different combinations, they give rise to what we call local climate zones. No? So we have done some studies on that to map these local climate zones. Local climate zones are basically urban and rural areas which are characterized by localized climate conditions. So these localized climate conditions are arising from the different geometric, surface cover, and thermal properties. In this figure, we can see representations of different local climate zones: compact high-rise, compact mid-rise, compact low-rise, open high-rise, open mid-rise, open low-rise with varying levels of vegetation, lightweight low-rise, and so on. And even bushes, scrubs, low plants, bare rock, and pavements, and so on. You can imagine that with all of these combinations, with all of these configurations, you will have local climates which are very different for these different areas. So if we look at again Quezon City and examine the different elements, the sky view factor, how open is a particular area to receive solar radiation, the surface albedo, the how much energy it can reflect away or absorb, and also the building surface fraction, the previous pervious surface fraction and pervious surface fraction, which are essentially the vegetation areas. And we can also have to include the building heights, as well as the roughness level of these different areas within, say, around 500 meters or so neighborhood effects. We can produce what we call these local climate zones. So for Quezon City, these local climate zones have been identified. 7 out of the 10 built up local climate zones and 6 out of the 7 land cover climate zones. Okay. And we can see those red areas, those are the compact high rise to low rise. So these are what the local climate zone areas would look like in a particular image. So you can examine the local climate zone represented, for example, by Eastwood, local climate zone 2, local climate zone 3 by Cruz de Ligas, and different other local climate zones with different levels of vegetation and height of these structures. And for the vegetated areas, we can see different configurations as well. Trees dominated, as well as those with shrubs and open areas, including also water areas. So if we summarize the daytime land surface temperature, we can see that the compact low rise and the densely built houses, areas dominated by these densely built houses, would have the highest daytime LST. The lowest daytime LST can be found in areas with dense trees, and as well as in UP Diliman campus and also the La Mesa watershed. This one. Okay. If we look at the nighttime, it becomes a little bit different. Water is now one of the warmest because of the heat retention. Is very low dissipation of heat, as well as the high-rise to mid-rise styles, so having the highest nighttime land surface temperature. And the lowest, again, will be the dense trees. The bare soil are areas which have dissipated all the heat they stored in the daytime. Will have now also one of the lowest nighttime LST. We are also doing at smaller scale or certain parts of the city, microclimate modeling and simulation using NDMet. So here we are going to simulating wind patterns as well as the differential heating of these different surfaces and exploring mitigation options that local government units can use. As mentioned, we are also looking at impact studies. What are the impacts of urban heat islands on water consumption, on electrical power consumption, on the transmission of vector-borne diseases such as dengue, on the thermal comfort, which is very important if we want to make our cities livable or more livable, and we also are looking at heat risk assessment. So we have conducted thermal comfort surveys in the different areas, and we have used GUHeat or Open Data Toolkit for collecting or implementing the questionnaires and doing the interview with the different people, no, in the streets. According to their age or according to their activity, we ask them of their thermal comfort they are experiencing. So Project GUHeat is producing a lot of products that can be used, or that will be used for sustainability. So we have developed the Google Earth Engine application called GUHeat Engine. So this will be used for generating automatically the land surface temperature mass, not only for the 7 cities, but for the entire Philippines now. And it can be done every time there is Landsat coverage within a particular area. Okay. So that's all. So thank you very much. So that's the introduction of our project GUHeat. Maraming salamat po.